brain signals. And the main domains, what we had covered are frequency domain, time frequency domain, as well as processing of features along the spatial domain. Today, we are going to start with another category of feature extraction process that pertains to brain connectivity networks. So, before starting with the concept of particularly brain connectivity networks, we are going to have a brief round of brush up on the basic preliminaries of graph theory. I mean, the concept of basics in graph theory you are already familiar with, you must have studied in mathematics, but still we are going to have a basic brush up. Then we'll focus on to the graph theoretical models of brain networks. Okay, so let's revise the basic preliminaries. So if I'm talking about a graph, all of you know that a graph is mainly composed of two components. One is called the node or the vertices. This is the first component. And the connection between the node or the vertices, they are referred to as edges or links. So a graph G can be said that it belongs to a set of vertices and edges, right? So diagrammatically, how does a graph look like? So we can have a set of nodes like this. So these are your nodes or vertices, and the connection between these nodes, these are your edges or your links, right? Now, graphs can be of two types. So the category of different types of graphs can be based on certain characteristics. The first characteristics is depending on the directivity of edges. So under which we can have two basic categories. Either the graph is undirected, that means if I have these nodes, the nodes are simply connected by edges which do not have any direction. So it's an undirected graph. Or it can be a directed graph. That means the links will have some direction. Okay. So this can be the two categories depending on the directivity of edges. The second category depends on the characteristics of the weights of the edges. So under this, we can have an unweighted graph. That means basically the edges have binary weights. So if there is a connection, there is an edge present, the weight W is equal to 1. If the edge is absent, the weight W equal to 0. Simply a binary graph. Right? And the second type can be a weighted graph. So your edges will have some weights. Apart from being binary, it can be binary, it can be something else. So again, if the edge is present, we can have different types of weights like 0.21 and so on. And if the edge is absent, of course, the weight is always 0, right? So this is the category of unweighted and weighted graph. What I explained right now equally applies for directed graphs also, right? Okay. Now there is another very popular concept in graph theory, that is the adjacency matrix. So anybody can tell me what is the adjacency matrix in graph theory? You must have studied it.
Matrix visualization of the graph.
Right. So basically it's a matrix tells me which nodes are connected to which other nodes via links, right? So this is a way, or rather a matrix representation of the connections between different nodes. So if I'm considering an adjacency matrix, if I'm talking about binary graphs only, so the row and column value, if that is 1, that means of course an edge is present. And if aij equal to 0, that means the edge is absent. So this concept, I can represent it via an adjacency matrix. So suppose let me draw a simple graph. Okay. And if A is my adjacency matrix, how do I write that? So I have to check how many nodes I have for this graph. I have 3 nodes, 1, 2, 3. Again, along the column, I'll have 3 columns, 1, 2, and 3. Now I'll check that if there is a connection between 1 and 1, no connection. So it is 0. Between 1 and 2, yes. 1 and 3, no. Then 2 and 1, yes. 2 and 2, no. 2 and 3, yes. Again 3 and 1, no. 3, 2, yes. 3, 3, no. So this is an adjacency matrix. If you have a weighted graph or a directed graph, accordingly you can just put the weights instead of binary weights. You're going to have some value 0 0.5, 0.4 and so on, right? Okay. Now, of course, in graphs, we also have a concept of self loops. So for this graph, suppose you can have a self loop like this, right? So if you have a self loop, then accordingly in your adjacency matrix, for 1 and 1, you're going to have some value, say 1, and so on and so forth, right? So now the question is, what is the significance of self loops? So self loops can represent any kind of feedback path or any kind of recursion based behavior, like you have studied recursive functions, right, in C or any other programming language, a function that keeps on calling itself, right? So to describe those type of relationships, we can use the concept of self loops. Okay. So we had a brief introduction to the basic preliminaries of graph theory. Now we'll specifically move on to the concept of brain networks, that means how we will utilize this concept of graph theory to eventually build a graph that represents the connection between different lobes of your brain. All right. So now we move on to the concept of brain networks. Okay. So when I'm saying it's a brain network, if we start with the beginning, like I said, a graph will have two main components, a node and the edges. So in brain networks, what does a node signify? A node signifies your brain lobes or the Brodmann areas of your brain, right? You know what are brain lobes, what are Brodmann areas. We have discussed that in the first class, right? And the second one are your edges. So in a brain network, what does this edges signify? They simply signify the connections between the brain lobes or your Brodmann areas. All right. Now, this is something we understand fine. We have certain nodes that is signifying the brain lobes, and the edges are denoting the connection between the brain lobes. And of course, in case of brain networks, we have to keep one thing in mind. So, notice that self loops are not present in brain networks. Because if I'm saying that a particular node has a self loop in a brain network, what would that signify? That signifies that that particular lobe is sending information to itself again and again. That makes no sense in real life, right? So one brain lobe will send information to another brain lobe. It cannot keep on processing information by itself again and again. So it is definitely not going to have any self loops in normal condition, at least for healthy patients. Okay. So in case we encounter any self loop, like if you're converting your brain signals into brain networks mathematically using any algorithm, if we encounter any self loops, we usually delete it. Okay. So keep that in mind. All right. Now the question is, we have a particular data set. So we have discussed in the previous classes, what is the structure of a data set? Any brain signal based data set. So we are going to have the channels over here, channel number 1, channel number 2, and say channel number n. And over here, 1, 2, 3, 4, we are going to have the data points. Okay. So it is basically a K cross N matrix. So this is the structure of a brain signal based data set. That is what we have in our hands. We know how to pre-process the data set. So we have the data set, that is step number 1. Step number 2, of course, we are going to pre-process this data set to remove different types of noises. That means we are trying to remove different categories of artifacts. You know what their different categories of artifacts are. We have physiological artifacts and we have technical artifacts. So that has to be removed. And we have discussed about those detailed algorithms, how to remove those type of artifacts, right? Now the third would be, you have to convert your data set into brain networks. Once you have done that conversion, the fourth step would be, you have to extract some features. So feature extraction from these brain networks. That would be your fourth step, right? So first two step is done. We first discuss with the third step, that is the convert the data set into brain networks. So we begin with this topic, that is formulation of brain networks. Now, the main objective over here is that we initially have a K cross N matrix. That is our original data set. Even after pre-processing, we have the same K cross N matrix. Okay. I have to convert this K cross N matrix into a N cross N matrix. Why? Because if you look at this data set, so these channels are what? They are basically your brain lobes. You're connecting each and every channel to specific brain lobes. And brain lobes are what? Your nodes. So what does your adjacency matrix denote? They denote the connection between different nodes. So this N cross N matrix is your adjacency matrix, where you have different connections between your channels, and channels are nothing but your brain lobes, and which are basically your nodes. So whenever you are converting your data set into brain networks, remember your channels are your brain lobes, and those brain lobes are getting converted into nodes in order to identify the connection between the brain lobes. So channels, brain lobes, nodes, these three are all same. Okay. Now the main motivation of getting this particular adjacency matrix is to first mathematically convert, or rather mathematically we have to evaluate the relationship between different channels, which are nothing but your brain lobes or your nodes. So this is my main objective. Mathematically, I have to evaluate the relationship between different channels, which is in my hands, right? So there are different techniques of converting, or rather evaluating this relationship. Let us begin with it. The first technique you must have studied or you must have heard in statistics or mathematics also, which is referred to as Pearson's correlation coefficient, also abbreviated as PCC technique. Okay. Now this particular technique provides you time domain based information, because it simply analyzes the correlation of every pair of channels obtained in time domain. So basically you're obtaining the correlation between every pair of channels. So how is it evaluated? So this is first point and this is the second point. So mathematically it is given as this. So over here your X bar and Y bar are the mean data point values for channels, respective channels X and Y, right? Next, your Rx and Ry are your standard deviation values for channels X and Y. And H here represents the total number of data points. So finally, from here you obtain your output will be a N cross N matrix. So channel 1 to maybe channel N, again channel 1 to say channel N. So it's an N cross N matrix, and you will have certain values. and that will help you to draw your connectivity graph, because you will get the answer like which node is connected to which, and you can easily draw your connectivity map. Okay, so this is one technique, the PCC technique, and this only provides me the connectivity information in the time domain. Now let us see, if I want to understand the connectivity information in the frequency domain, then which particular type of method can I use? So this was point number 1. Point number 2 is the magnitude squared coherence, MSC. So this also gives you the relationship between different channels, but it basically depends on the frequency domain based information, not the time domain based information. Okay, so what is its mathematical representation? So it's in the frequency domain. So here we have studied in the last class, this denotes the cross spectral density. That means basically the power spectral density between channels X and Y. And Sx and Syf are the individual power spectral density pertaining to channels X and Y. And how do I evaluate the cross spectral density? Basically, it is the frequency components of channel X and the conjugate of the frequency component of channel Y. This is it's mathematically defined. Okay. Again, the output will be a n cross n matrix denoting the relationship between every pair of channels, but in frequency domain. Okay. Now, the third type of method, which you are kind of familiar with, that is the wavelet transform coherence, WTC method. So in the last class, we had a discussion on what are wavelets, and the information we obtain from wavelet is time and frequency domain based information on the same platform. So we basically choose a mother wavelet, and then we either expand or compress the mother wavelet in order to obtain parallel time and frequency domain information, right? We had discussed that in the last class. So mathematically, how is wavelet transform coherence defined? So we have both the components, time and frequency. And then we have the individual wavelet transforms. Okay. So here S is nothing but the smoothing operator. So you can use any type of smoothing operator of your choice, maybe a Gaussian smoothing operator or Laplacian smoothing operator, that will help you to either expand or compress your mother wavelet, right? And your W, X function is basically your wavelet value pertaining to your X channels, and WY function is your wavelet value pertaining to your Y channel, and this particular part is basically your cross wavelet transform. Okay. So you can use any of these three methods to convert your pre-processed data into your adjacency matrix, which will ultimately help you to draw your brain connectivity network. That means now in your hands, what you have as an output, you have your adjacency matrix, right? Or you can say it's a connectivity matrix. You know which node is connected to which particular portion. Now in brain signals, if you have to finally make the connectivity matrix in a particular process. What is that? Of course, you have your connectivity matrix or the adjacency matrix in hand because you already know what is the relationship between every pair of channels, right? So what you can do is, so right now the example I'm considering is with respect to binary undirected graph, okay? Just to make the process very simple. So for this, the adjacency matrix, the final adjacency matrix can be made in this following way. So your matrix value is 1 if any of your components, like if you're connecting your graph, or rather you're evaluating your adjacency matrix using Pearson's correlation or using magnitude square coherence or wavelet transform coherence, anything, okay? So the value is going to be 1 if this particular value, which can be your wavelet value, which can be your magnitude coherence value or your Pearson value, is greater than tau. What is tau? It is a predefined threshold. Or it is 0 otherwise. And the second way what you can create the final adjacency matrix is, if you want to make it a weighted graph, weighted undirected graph, then you can keep your values, what you have obtained from wavelet or squared coherence or Pearson, if that evaluated value is greater than tau or it is 0 otherwise. So tau is the same thing, that is a predefined threshold. That means in these two basic steps, so this is your final step of adjacency matrix computation, where you are performing what? Some kind of a thresholding. Now the question is, you already have the different relationships between the channels, that means the lobes, you have those relationships, right? So you can directly put them in an adjacency matrix. Why perform this thresholding? What is the significance of this? That is a very major point, isn't it? Why are we doing this extra step? So what is the significance of this step? This step is very, very important when you are building a brain network. If it's a different network, then that's a different thing, right? So since we are building a brain network, sometimes what happens is that there are edges which are very weak edges, okay, which has been built due to noise. Of course, we are pre-processing the brain data via a lot of algorithms, but no pre-processing step is 100% pure, right? I mean, theoretically, of course, we can understand it can be 100% correct, but practically, no signal can be 100% noise-free. So there can be some weak edges created due to the presence of the remaining noises, which leads to some spurious connections. This is the term utilized. That means they are unwanted, redundant connections. Okay. So that is why we require any kind of thresholding depending on whether we are creating a binary undirected graph or a weighted undirected graph. We need some amount of thresholding to remove those spurious edges. So this is very important in case of brain networks. We do not need those relationships. They are not important. Okay. Now the next question is, fine, we are going to perform thresholding. We understand what is the significance of thresholding, but how to choose this value of the predefined threshold? So choosing the predefined threshold. How to do that? Now the main objective over here is it depends on the cognitive task performed. So under this, I can broadly have two scenarios. First one is that if I have to distinguish between healthy and disease subject. If this is my objective, that I have to distinguish between healthy and a disease subject via clustering or classification, whatever it is, then generally you can keep any value of tau. The default we keep is 50% edges. You can increase or decrease this value as per your wish. Why is that? Because generally, healthy people, the brain connectivity is quite dense, and for disease people, the brain connectivity is very sparse. That means all the nodes are hardly connected because they are already diseased patients. Their lobes are not functioning properly, and hence they are not able to transform maximum number of information among themselves the way it happens for healthy people, right? And that is why whatever value of threshold you keep, be it 50%, be it 20%, 30%, you will always get a very dense network for healthy people and a very sparse, that means a very less dense network for diseased people. This is first scenario. The second scenario that can arise is that you have to distinguish between different categories of subjects. All of them are healthy. So over here, your main task is not to categorize between whether a person is having some disease or not. That is a different experiment. Here you have to categorize all the subjects, I mean different categories of subjects you have to distinguish, and they are not diseased. Everybody is healthy. So what can be the experiment on this? For example, you can have three categories. You are checking the creative level of subjects. So whether it is low creative, medium creative, or high creative. So everybody does not possess the maximum level of creativity. That varies from person to person, right? So suppose you are testing these things, low, medium, and high levels of creativity in a person. So this has nothing to do with diseases. It doesn't mean a person who's low creative means a person is diseased or has some brain problem. No, right? They're all healthy subjects. So in this case, how would you choose the value of tau? So here, the value of tau is chosen in such a way such that all the brain networks have fixed number of links. So that means, suppose for low creative, it might happen that the value of tau is 0.3, say for instance. For medium creative people, you are choosing the value of tau is 0.8, and for high creative, the value of tau is 0.5. If this value of tau is kept, then the total number of links for all the networks, for all categories of networks, is say 100. So you have to manually find it out, what is going to be the correct value of tau for each and every category, so that the total number of link, they add up to be the same. So why are we trying to do this? Why are we keeping this condition? Because for healthy subjects, if I have to make the networks comparable, I need to have fixed number of links, because all of them are healthy subjects, right? So if somebody is having very dense connection, somebody is having a very sparse connection, I cannot compare them properly, because dense and sparse connection comes into scenario if I'm categorizing healthy and disease subjects. And I can also emphasize, see, if this person is diseased, that is why it has less connections. But here everybody is healthy, right? So that is why I have to somehow manually find out the different values of tau, which will ultimately give me fixed number of links for different categories of networks. Is this part clear to everyone? Any doubts still here? Okay, very good. So now we have formulated our brain networks, right? So the third stage is over. Now we have the fourth stage, is that we have to extract features from the formulated brain networks. Okay. Now the question is, fine, the brain networks are built on adjacency matrix. We know that which node is connected to which node. Why do we need to again extract separate features for it? So over here, when you obtain a particular brain network, you can just see the connections, right? That is known to you. You have your adjacency matrix, you can just see the connections. But from here, you can just have a qualitative evaluation. That means just looking at the connections, you can just say, fine, these nodes are having a lot of links. These nodes may have little number of links. So you can have just a brief qualitative evaluation of your brain networks. The brain networks are quite complex to even look at, right? So just I'll show you one picture of a brain network. This is from one of my papers. So it's something like this. Okay, so there are so many nodes, so many connections. So you can maximally say, okay, node number 10 and 7 is having less connection. Node number 12, 14, they have a lot of connections. So you can just provide a very qualitative evaluation of your brain networks once you have it via the adjacency matrix, right? Apart from that, you cannot make any kind of evaluation. But if you want a very quantitative evaluation, right, mathematical quantitative evaluation of the brain networks obtained, then you have to go for feature extraction. So let me go back to the digital board. Yes. It will vary from person to person. But if like there are 3 people, they fall under the same category, like same class, then there will be mild variation, but it will be almost same. Getting my point? Okay. So like you've seen, the brain networks are quite complicated. So in order to have a quantitative evaluation, Yeah, but this is like, I'm talking about one brain network of one person, right? But if you are taking multiple number of trials, so for each trial you'll get a brain network for different tasks. So suppose you have 100 trials, you'll get 100 brain network for one subject I'm seeing. Then you will have multiple sessions. Then you have to perform these sessions in a day. So around you are going to have 20,000 brain networks per subject. So you have to perform this experiment on 50 subjects. Now imagine how many number of brain networks you are dealing with. So just by getting a rough eye estimation of these edges, it's getting impossible. I just showed you one picture. Getting my point? Okay. So you need some kind of a quantitative evaluation of the brain networks acquired. Now, again, what do I mean by this quantitative evaluation? What is the objective? What do I want to perform from here? My main objective is to identify the hub nodes. The question is, what is this concept of hub? If you have studied communication networks, you must have heard about hubs, but still I'll discuss over here. What do you mean by hubs? Suppose I have a network like this, a simple network. Right? So that means over here, if node number 1 has to send any information to node number 5, it has to pass through node number 3. Again, if 2 has to send any information to 4, again it has to pass through node number 3. Okay. Again from 2 to 5, again it is passing through node 3. That means in this diagram, node number 3 is acting as a central controller of this entire network. And this has a particular term. This is referred to as a hub. Okay. Now the brain network I showed previously, directly you cannot identify a hub just by eye estimation, right? Because it is not a simple structure like this. Over here you can easily identify 3 is a hub, right? So that is why we need some quantitative evaluation, because these hubs are the most, yeah. No, what I'm saying is like, just by eye estimation, it will be very difficult because you have so many networks across trials and across sessions and across experimental days, right? Yes, that is what I'm trying to say. Okay. So that is why you need some quantitative evaluation, some mathematical formulation. That is simply, if you just put that into your program, that program will give you an output. So you don't, it is going to be very tedious if you are dealing with so many number of networks. So we are going to deal with 2 types of important features that helps us to identify a hub. The first feature is degree centrality. So degree centrality is defined as this. That means it is basically, for a particular node, it is simply the number of links connected to that node. So if you have this type of a graph, so the degree centrality value of node number 1 will be something 3. So it's a simple thing. Now, it is not always necessary that is a particular node having a large number of degree is necessarily going to be a hub node, right? That is why we generally do not utilize a single feature for drawing this conclusion. We at least extract 2 minimum type of features. The second feature is a betweenness centrality. And this helps us to mathematically evaluate the hub value more appropriately. So let me write down the mathematical evaluation, then we'll solve a small problem on this. So suppose the betweenness centrality of say node number V, it belongs to these vertices. We have the value as sigma u. Okay. Now what are these terms? So I'm writing them down. This denotes the total number of shortest paths between any node u and w, and sigma uw of v means total number of shortest paths between u and w that passes through V. This is the definition. Now let us take a small mathematical example to check how would I perform this. So let me first draw a sample graph. Okay, so this is a graph suppose provided to me. Now I can find out, see, by looking at this graph we can understand the hub nodes are C and D, of course. But mathematically how can we prove that? So suppose I'm going to find out the betweenness centrality value for node C. Okay. So first what you have to do, you have to make, you can just write down the question so that you can just keep on tallying with whatever I'm performing. I'll just wait for 2 minutes, you can just draw the graph. I hope all of you have drawn the graph, okay, as I'm proceeding. Okay, you have to make 4 columns. First is node pairs. Next, this term sigma uw, what was there in the formula. Then sigma uw of v, and then the ratio sigma uw of node v divided by sigma uw. Okay. Now, the trick over here is that since you are finding out the betweenness centrality of node C, you will find out the node pairs excluding node C. Okay. So, your node pairs would be something like this. First, it will be AB, AD, AE, AF, BD, BE, BF, next you will have DE, DF and EF. Okay. All right. Now, how to perform this or fill up this table? So, sigma uw, this means that I have to check whether there is a shortest path between node A and B. Between node A and B, yes, there is a shortest path. There's only one shortest path, right? Total number of shortest paths. So, one shortest path is present. Now I have to check for the the third column. Now, does this shortest path pass through C? Does it pass through C, A and B? Yes or no? No, right. So this value would be 0. So ultimately the ratio will be 0. Okay. Now being coming to A and D, do we have a shortest path? Yes. How many shortest path? Only one. This one. And does it pass through C? Yes, it passes through C and hence the ratio will be 1. Okay. Again, if I'm considering A to E, yes, we have a shortest path. Does that shortest path pass through C? Yes. So the ratio will be 1. A to F, shortest path is present, total number is 1. Does it pass through C? Yes. Ratio is 1. B to D, one shortest path present and it passes through C. Ratio is 1. Next, B to E, shortest path present, passes through C and the ratio is 1. B to F, one shortest path, passes through C, ratio is 1. Coming to D to E, we have one shortest path. D to E shortest path does not pass through C, so the ratio is 0. Again, D to F, one shortest path present, does not pass through C, ratio is 0. E to F, one shortest path present, does not pass through C, and hence the ratio is 0. Is this entire table clear? Any doubts? Yes. Okay. Now what you have to do is just add the last column. Add the values, tell me what you're getting, because you have to take a summation via this formula, right? To take the sum of this ratio. What is the final value of the last column? 6, right? So the betweenness centrality value of the node C is 6. If in the same process, if you calculate the betweenness centrality value of node D, which is also a hub node in this case, that will also be 6. But if you calculate the betweenness centrality value of other nodes, which are not hub nodes like A, B, E, F, they are going to have a less value as compared to C and D. So from these quantitative values, you can understand that which particular nodes are acting as hubs. And once you identify a node acting as a hub, that means that particular brain lobe is the most activated brain lobe for your cognitive task. So that is the most important conclusion which is required for your brain signal processing. Okay. Now I'll take another short example of this betweenness centrality. Yes, through that also you can understand that which particular nodes is acting as hub. That is also another different approach to check which shortest paths are present between which nodes. Then you have Dijkstra's algorithm also, you have studied in graph theory. That also can be applied. There are different techniques for it. This is the most simple, most technique, and rather this is a more modern technique, I would say. Okay, so this, the Dijkstra's algorithm and those spanning tree algorithm, Bellman-Ford's algorithm are the older ones, but they are equally applicable. Okay. Suppose I'm taking another example for this betweenness centrality. Just draw this graph so that this problem becomes very clear to all of you. Okay. So again, we have to make those 4 columns. Suppose I have to find out the betweenness centrality for node A. So note pairs. Okay. So your note pairs will be B and C, B and D, BE, BF, CD, CE, CF, DE, DF, and EF. So looking at the graph, first B to C we have one short path and that does not pass through A, so the ratio is 0. B to D, again you have one shortest path, does not pass through A, so the ratio is 0. B to E, you have only one shortest path and that does pass through A, the value is 1. Coming B to F, you have one shortest path, it does not pass through A, the value is 0. From C to D, you have shortest path, does not pass through A, so the value is 0. Next, you have the concept of C to E. You have one shortest path, does not pass through A, ratio is 0. C to F, you have one shortest path, does not pass through A, the value is 0. Now coming from D to E, look at the diagram carefully. For D to E, you have two shortest paths, one from D to B to A to E. This is path number 1, right? And again from D to C to F to E. This is path number 2. So D to E you have two shortest paths. That is why I took this example, okay? So in this case, D to E you have two shortest paths. How many times it is passing through A? Only once. So the ratio is 0.5, 1 by 2, right? Again D to F you have a single shortest path, doesn't pass through A, it is 0. And E to F you have a single shortest path, doesn't pass through A, the ratio is 0. What is the final addition? 1.5. So I hope you have understood how to solve this problem. I mean, it's a very simple thing. You're already familiar with graphs. So if you have any doubts for today's class, you can ask me right now. That is all for today's class. Okay. Yes. Yeah, you can mail me directly or you can also meet me. I mean, generally I'm kind of overloaded with classes. So even if you visit the department, I don't know you'll be able to find me or not because every day I'm having lots of classes. So you can come to the ECC department. There's no harm in it. But you can also mail me. I'll reply it. Okay. And like I have already announced in the through via mail that for the class test thing, I'm not going to take any class test. I'll be providing a very short assignment which you have to solve within 4 to 5 days. And you're just going to scan the pages and send it to some email which I'm going to provide later. So this will take, this assignment I'll provide roughly around the end of April, maybe on 27th or 28th April, okay, around that time. So do not worry about the class test evaluation, okay. So in the next class, we'll start, the feature extraction part is over. The next class, we'll start with the feature selection part, classification and clustering, okay. So thank you all of you.